No, yes. Well, good morning, everyone. Today, we have a session by Dr. Mayank Tiwari from IIT Patna. And we welcome all the participants to this session. And this session will continue up to 12:30 p.m. And after that, you have a demonstration by Dr. B. Venkatesham from IIT Hyderabad on vibration control and acoustics. A small demo is planned. And after that, we have the final valedictory session at 1:15. And we request all the participants to stay there and give your valuable feedback on the sessions. Sir, Dr. Tiwari, sir.
Yeah, Dr. Bhanu, just give me half a minute. I'll be ready.
Okay, sir. Okay, sir. Okay, sir.
Yeah, please let me know if you can see my screen.
No, sir. Say we are unable to see your screen, sir. Yes.
It's there now?
Yes. Now, yes, sir. Now it is okay, sir. Sir, first of all, let me introduce you to the participants, sir.
Yeah, please.
Yeah. Today, it's an honor to have Dr. Mayank Tiwari for our session. Dr. Tiwari is an associate professor in the Department of Mechanical Engineering, Indian Institute of Technology, Patna. And, he's an expert in tribology, rolling sliding wear, fretting, vacuum tribology, rotor dynamics, and nonlinear dynamics. Dr. Tiwari is a PhD in nonlinear dynamics, and he worked in Tata Motors, General Electric R&D, and General Electric Aviation. He worked on development of bearings for X-ray tubes and wind turbine drive trains. He's an expert in Six Sigma black belt, and he's a black belt there. And he has more than 30 papers in reputed international journals and 10 patents in US, France, and India in the area of tribology, dynamics, and acoustics. So this will be a very valuable lecture for all of us. It is a nonlinear dynamics in rotors. So now we welcome Dr. Tiwari, sir, to take on the session. Welcome, Dr. Tiwari.
Yeah, thank you,
sir.
Dr. Bhanu. Can you all hear me?
Yes, sir.
Okay. I would just request you, Dr. Bhanu, to give me a heads up after 1 hour. I think this is a 1.5 hour. How long do you want me to go?
Okay, sir. It's this up to you, sir.
No, I mean, we can have about 10-15 minutes if required of questions. So I'll finish at around 1 hour. Is that okay?
Okay, sir. Okay, sir. No problem.
Yeah. Just give me a heads up when it's about an hour, Dr. Bhanu.
Okay, sir.
Thank you. Okay. Good morning, everyone. As Dr. Bhanu has been kind enough to invite me also and introduce, I'm basically a background from the industry and spent about 14 years in industry, still working with industry on some projects. So a combination of tribology and rotors, and when we study design uh, or teach design to our students, we will see that there are so much of overlap between tribology, bearings, gears, and rotors. So you can, logically understand where my experience comes from. That when you start developing a product which is in the area of, you know, X-ray tubes, perhaps some of you may not be aware that the X-ray tube has a very high-speed rotor inside vacuum. So once we started working, then we came to the most challenging problem of mechanical engineering. How do you make bearings run in vacuum in space? It has a lot of implication for aerospace applications. So that's where my experience comes. And when you run any mechanical system at its extreme, either it's the extreme displacement, speed, stress, strain, you go into nonlinear domain. So you lose on elasticity, you go into plasticity. So nonlinear dynamics in rotors is very important, and we will see why so. So if you see rotor dynamics, I'm sure many people would be aware of this, and you would be teaching. But it is actually a specialized branch of applied mechanics and rigid body dynamics actually. So there is a very high speed set of rotors in systems like gas turbines, aero engine gas turbines, in turbo pumps, in superchargers, and many other applications now, as I told you, X-ray tubes. So the technology currently is running on rotors, if I can say so, because you're getting your power out of it, right? You're getting locomotion out of it. You are getting your, things like the cryogenic engine of your GSLV is running on turbopumps. So rotor is very important. It can be non-critical also in your house water pump, where you really don't care about too much of noise also, or if it fails, you can replace the pump. But now more and more so, the technology, critical technology, it is assuming a very important form, and we really need to go to the understanding the extreme, the domain of design for rotors, so that we don't have catastrophic events like failures, such as in aircraft engines. So the understanding of nonlinear dynamics in rotor, assumes a huge form. Just for a little history, and this is from my, great master from India, Professor J.S. Rao, late Professor J.S. Rao, who's there in IIT Delhi, and he guided me on a number of things and guided many people. So I have taken this from his one of his last lectures actually with us. He passed away last year. So, rotodynamics history starts from even before Rankine. We all know the name Rankine, 1820 to 1872. It's actually started with human beings in Egypt when they started rolling huge logs of stone on, wooden logs. So you had something rotating. So rotodynamics started there. But then when you looked at around 1800, when industrialization was happening, so, scientists like Rankine studied the rotor. Then almost a little in parallel, but after that was De Laval in Sweden. And there is a huge controversy on who made the first, power turbine, but De Laval had as a huge contribution in terms of the turbine and the rotors. And these were moving at very high speeds. They were moving at 10,000 RPM at that year. You can see it is 1845 he was born. So in about 1913s, we had a very high speed turbine. And what happened was that at that point of time, it was running, in fact, if you see 1883, 40,000 RPM. So we had gone to very high speeds at that time. But what happened was when he did this analysis, he found that the displacement of the rotor has this in denominator, and this can go to zero, right? This is the running speed, this is the stiffness here, and this can go to zero. And if we don't avoid this, you can have an infinite displacement. So at that point of time, it was assumed that no system can run beyond your resonance, which is what this formula is telling us. So it's interesting to understand that, many things which we take just now that it is not possible in the world may become possible after 50 years. Same thing happened there. In 1883, 40,000 RPM, people must be running around, huge, very fast thing. And now 40,000 RPM we can have in small machines in the house also now. Almost, not 40,000. But the point is that technology is growing. Our knowledge, such as what we are discussing just now, can lead to the impossible becoming possible at some point of time. But you can see that in 1800s, this seemed to be impossible. Then Parsons in 1884, at the same time, made one of these turbines. This is another Parson turbine which you would have made. And they were actually, what they were looking at was, of course, to avoid the natural frequency, otherwise the amplitude was going high. Systems with low noise and more power production, so more torque, and they had to drive a generator basically. So then Edison came along, and of course he set up General Electric and did a lot of things, in terms of producing DC. And then there was the controversy of AC with Tesla. But now, what one of these contributions was actually electrifying the streets of New York with this turbine and this generator. And so a huge amount of analytical work in Rotors was done with him at that point of time to get these systems running for a long time. And it was, I think, called Jumbo, named, okay, and the constant voltage dynamo. This dynamo, this is the picture of that. And this is one of the earliest rotors, a full scale industrial rotor, which was set in by Edison. And then, of course, 1900s is when technology reached huge levels, and there was a lot of work being done in mathematics in Europe, and things were going very fast. And one of the bad byproducts was that we started fighting, and there was the First World War and Second World War. So it's it's not good, but I mean, we have to really accept the fact that a lot of technology which we use now developed through those wars. Hopefully we can, with this awareness, in future we can develop technology which is not developed through war. And this is actually the pivotal philosophy of our country. Or we might have forgotten it because we are overwhelmed by the American English and the Western philosophy as such. But the point is that technology developed and rotors developed in the First, Second World War. And then you had steam turbines through the 20th century. You can see huge steam turbines. I'm sure if someone of you would have visited BHEL or a steam plant, they are being made in India also. And they're of 1500 megawatts. The huge turbines which are running, and which needs to have very critical rotor dynamic analysis done. Otherwise, we will have huge amount of failures. So then you can see rotors of motor. Now, these are motors which are everywhere now, right? Even small drones have motors, toys have motors, our house pump has a motor, and then you have very high speed motors for specialized applications, and they are rotors actually, where actually if you see this clearance here, the clearance with the stator is very, very low. Okay, this clearance which I was just trying to draw here, 1 minute. If you see the clearance, so there would be a stator here, right? And there was, of course, magnetic and magnetic material here. So the clearance between the rotor and stator has to be very small so that it doesn't lose out on the power, because the flux has to be passed through and go from the rotor to the stator. Now that means that if this rotor vibrates and the vibrations are more than the clearance, you will have rub in motors, and they will fail immediately because these coils made of copper will just wear off and break. So, we have to appreciate the fact that even in very normal things like motors, it's important to have a rotordynamic analysis, else you're going to have a failure. By the way, motors, one of the issues is heating. If you touch a motor while it is running, there's a fan always to cool it. You can see the fan here also in this picture. This is to keep the temperature of the rotor down. Otherwise, it will expand and close the clearance, and you will have huge nonlinear effects due to rub between the rotor and stator, which we are going to discuss in detail in the models later. So, design of a motor is a huge part of it is rotor dynamics. Then, of course, came 1941. Again, as I said, the war, the Second World War, led to the development of the first jet engine in United Kingdom by Sir Frank Whittle. It's very interesting that although this engine was developed in UK, United Kingdom, but industrial production of the same kind of engine with the technology developed by Frank Whittle was actually done in United States of America by General Electric. So the rotor dynamics actually came to age. Very high speed, very critical, because you can't have it fail up in the air. People will lose life. And then all those developed into these jet engines, which we see now. So this is the Rolls-Royce RB211. Then there is, of course, the G engine. There is Pratt and Whitney, and a huge amount of technology. You can see the very complicated rotor stator here. There is actually rotor inside a rotor, multi-spool rotors which are there. And then there is a cantilever part to this, especially the blades which you see here, which you can see if you're boarding an aircraft. These blades, it's like a cantilever rotor with very, very small clearance here. The clearance is almost the size of a hair. And now if you have vibration going up, you will have these blades running at about 2000 or 3000 RPM, not more than that. They are very huge. They will touch the case. And of course, there is design done to prevent the failure. There is an abradable which is put there, which abrades on touch. But the touch itself is a huge nonlinear dynamic event which will create failure. And in fact, I will show you a photograph of a failure which happened last year, where the whole engine, there are lots of videos on YouTube where that huge engine just broke apart, 777, and it was dropping down on the ground on roads and houses. So these are very critical things which have been made. And the steam turbine, you can see this huge rotor here. This is the generator here. This is the turbine, different stages. So now this is again a long rotor, and these long rotors would have a problem of sagging. So this gravity plays a huge role in the analysis of this. And again, we don't want the clearance between rotor and stator to be high. Steam will leak and you will lose power. So this is again another challenge, but it is interesting that a lot of work has been done to overcome all this. And this is the work, fundamentally, which we are going to talk about today. Now you can see this kind of analysis which has been done on ANSYS, and this is, I should repeat that this is again a slide from late Professor J.S. Rao's presentation on ANSYS to find out the deflection and where is the mode and where is this blue part which you can see is the rotor, where it can touch the green part which is the stator. So anyone who's used ANSYS for these kind of simulations will understand that how much is the damping. This is a huge exercise in simulation of aircraft engines, because you will, if you don't put the right damping, you will get you might overestimate, and then what will happen is you will, the factor of safety will be very high, and you will have very heavy engines, right? Heavy engines means more fuel. More fuel means less money. So that's another fact of life for engineers, is that we can do a lot of things, but we have to be careful. We have to be within our money. Otherwise, we won't be good engineers. So that's what the whole point of engineering, industrial engineering is actually for us, the engineering in industry. So, these kind of simulations have to be cross-checked with a lot of experiments before you can actually have a design made. Okay. Now, again, picking up some very interesting things from his presentation. This is the cryogenic spatial, the pump for the GSLV which India has. This is interesting because this turbo pump is actually pumping liquid oxygen and hydrogen. You can imagine, we are talking of minus 180, minus 173 degrees centigrade. So the bearing and the rotor is actually facing temperatures of minus 173 degrees. And this is very, very high speeds. It can go to I think 50, 60,000 RPM or even 1 lakh RPM, facing such low temperatures. So the rotor has to be designed. The life of these pumps at this point of time is just 2 minutes, because the cryogenic stage actually just survives 2 or 3 minutes in space, and then it is ejected out. But then a lot of work is trying to be done for, if we can resalvage, because this is a very expensive thing and we are just throwing it out. That's why space technology is so expensive. So now bearing needs oil, it needs material which can run at such high speeds and low temperatures, right? It should not have a fatigue, because you can understand metals, most of the metals at that low temperature will just harden up and crack. Obviously liquids will just freeze up, so you can't use normal lubrication like oil in this. So the whole rotordynamics and tribology of this kind of rotors is very important, which is being done in India. I'm not saying that it's not being, because we have a cryogenic stage for the GSLV with us now. So this is GSLV, of course, a huge thing which has been done in India. And this is a photograph which I put from Professor Rao's presentation on, the where the stage is, and it is performing very well. I mean, we unfortunately had one failure just recently, but otherwise we've had very few failures of this stage in India. Okay. And of course, you can see these stages as they go. The liquid stages here, the cryo stages here. This is one of the last stage, as you can see. Okay, the liquid hydrogen and oxygen actually mixes to produce the thrust. And when liquid oxygen and hydrogen react, they produce water actually. Okay, so that thrust is creating, the output is water. It's high up in the atmosphere. So, and then it is ejected out. So we lose out on that very expensive technology. So this is more photographs of this, and actually it's interesting and also very enlightening for all of us that these are the kind of technologies which are being worked on in India, especially in the field of rotordynamics actually. And this is more photographs from the cryogenic stage. You can see the complexity of the fuel, and the other systems in this. It's not a very simple, just a rotor, it's a lot of things inside it. And then of course there's a test bed for that. And these tests are done in ISRO to find out the thrust and the safety of the whole engine. And then, as I told you, there's a lot of other work being done. For example, this is actually a torpedo for the Navy, where they are using these rotors to propel the torpedo. So this is another critical stage. This is called the Shakti torpedo, which has an impulse turbine inside it. So, we get some idea of the history, the importance, what's being done in our country. Now, the importance, this is the photograph I was referring to, which is the Federal Aviation Authority, which is the authority United States of America, and the amount of work they've done for safety and setting up standards for gas turbine rotors and other aero engine systems is now a benchmark for the world. The whole purpose for this agency is to set standards for safety. For example, one of the features they set is that this is the photograph of the 777 last year, which failed. And this whole cowling and the casing of the engine fell. You can see there's a fire, and this started because the fan blade actually touched the stator. And there was a huge amount of vibrations. The passengers inside were actually being shaken. But the FAA standard actually has gone through so many tests and design that the whole design is made for an aircraft engine to sustain these events, and the engine should not fall off. Right? I mean, the cowling and casing has fallen off because if the engine falls off, the whole aircraft will go through a huge unbalance and might crash. So and especially now when we are having long flights with just two engines. If you had seen a Boeing 747, it had four engines. So even if one engine failed, you were still on three engines. Now, with a lot of design and standards being set by FAA, long distance flights are being running on two engines, which basically means that if one engine fails, like in this case, the aircraft can run for 3 to 400 kilometers to the nearest airport with just one engine. In fact, the most important part of the aircraft rotor design is that it should not fail and break the engine out from the wing. So if you see this video, it's a photograph from a video. You can go to YouTube and see this. You will see that this engine was shaking, and I have a video here of this test, which is stipulated by FAA for each engine manufacturer. So let me see if this runs here. Well, this is a YouTube video again. You can go back and see, and this is the aircraft engine test, which is done after all the design. And finally, to prove it, and this is of course a destructive test, the engine actually catches fire. The engine is like billions of dollars, millions of dollars, and these are broken apart just for the sake of safety actually. Okay, so this is an important thing, and this is being done, and most of the important work in this is rotordynamics. That's the point. The blade, which is rotating with very high speeds, the stages of the compressor and turbine of a gas turbine, if they are touching. Then there is the bearing, which is inside the engine, in the compressor and turbine. Then it is also designed for events where if the blade breaks, then you suddenly have very high level of unbalance. So how do you contain that? So there are dampers which are put inside. So some of that picture I will be giving to you on specifically from the work I have and my team and my students are doing. Okay, we are not working per se on this whole engine, but we are working on rotors and parts of it. So let us now go to a little basics of nonlinear dynamics in rotors and see that there are various sources of nonlinearity in rotors. So as I explained to you, the events of the blade touching the stator, it is called rotor stator rub. Then there is the bearing clearance. Actually, the bearings which we use for our applications, even for common applications, they have some clearances. And once these clearances close up, the rotor is going to touch the stator, and you will have a lot of frequencies coming out which can be destructive. Now the rotors can crack and create a symmetry. This is very important because a symmetric rotor, it's like, if you make generally rotors are cylinders, symmetric cylinders. But very, things like even the rotor of a motor, a common motor has windings of copper. So not all of the rotor is made of steel. There is some part of copper. Now that copper has different density. It has different, so parts of the rotor are made of different density, so different mass, and parts of the rotor are made of steel. This creates a symmetry, and this asymmetry can, so a symmetric rotor running actually creates time varying stiffnesses. And time varying stiffness is again a source of nonlinearity, and something which we need to avoid because nonlinearity actually leads to unexpected results. Then journal bearings and squeeze film dampers. Journal bearings are well known actually, which also because of the Reynolds equation which we've done for design, they create nonlinear forces at some certain kind of operational speeds. And squeeze film dampers. These are the dampers which are put in ball bearings of aircraft engine. So some of these things we are going to discuss as we go along. So this is the work, I'm coming now a little bit into details on the work we are doing. So if, we assume a rotor, and this is of course called a Jeffcott rotor, another great scientist for rotor dynamics who, started doing the analysis assuming a symmetric rotor with a disc in the center. Okay. And this rotor, like the aircraft engine, is inside a casing, which is these two lines here. The lines here. This is the stator actually. And this is the clearance given by R0. So this rotor has this clearance, and if, because of unbalance E. So the unbalance in a rotor, which is an unavoidable thing due to manufacturing errors or with time, the actually the CG of the rotor, which should actually be here, can move here. For example, certain steam turbine rotors have some kind of fouling. Fouling means some amount of dirt or something collects on the blades. So the CG by just small microns moves from the center to one side. So that eccentricity is called E. So the unbalanced force is me omega square, and this of course we can derive, it's the centrifugal force, and this centrifugal force acts out like this. It has a contribution me omega square cos omega t in the x direction and me omega square sin omega t in the y direction. So one is here and the other is component is here. So we have this 2 degrees of freedom system. And in this, the important thing is that we are now having these two, of course, this is our general mx double dot cx dot plus kx, where k is probably your spring stiffness, I'm sorry, the support bearing stiffness. But because of the touch, because of the rub, what is happening is that we are having the fourth term in this coming up, which is here. This term here. This term here and the term here. These. So this term is coming because this part, this rotor is going and touching the stator during whirl. So it whirls. Now for many people, I'm sure you have gone through this. The whirl is actually a motion which is similar to that of the earth going around the sun. We are going around and we know we go around in a year, but we are also rotating in 24 hours. So the rotor actually turns on its axis, and this axis goes around the center, which is here, and this going around like the earth going around the sun in a year is called whirling, and the earth rotating on its axis is called rotation. Same thing is happening because of rotors, and the main cause for that is the Coriolis force, which acts on rotors to make it go on the side, and the whirling starts. Now that whirl, if it brings the displacement of the rotor in a direction which is, this is actually under root x square plus y square. So if your motion is like this is r. So this, the contribution here is x and this is y, right angle triangle, x square plus y square is equal to r. Now if that r is actually greater than r0, which is the clearance, that means the rotor will touch the stator, and this h which you see here is the Heaviside function, which tells you that this will be a quantity which will be like 1. And then since the rotor has touched the stator, you will get friction force, which will lead to the effect due to friction force, and of course the stiffness of the stator, which is Kc. Okay, so if we see this in detail here, so the rub contact forces actually are due to radial motion. Okay, now this is the tangential force due to friction. You can see it acts in the direction opposite to the surface velocity of the rotor, Pt. And there's a normal force, of course, Pn, because you are going and touching a stator. Now both of these forces have components, as can be seen here. So these components, now of course, Pt is equal to mu into Pn, right? Mu into normal force is the tangential frictional force. So each of this has x and y component. So Pt has x component and Pt and Pn have x and y component. So we can get Px and Py. Cos theta is at any position x by r and sin theta is y by r. And r is equal to, as I told you, under root x square plus y square. So from the above equation, Px is equal to, if we put for cos theta and sin theta, we will, if we put for cos theta, sin theta and cos theta here, we will get the equation which is shown here. Okay, so Now, when we convert this into Pn being the normal force, and we will get Rpx. Okay, so sign of V velocity is to accommodate change in friction direction, which is a result of the relative velocity. Now, the relative velocity is because of, as I told you, the Earth rotating on its axis, which is the rotation. So, the surface of the Earth or the surface of the rotor will have some relative velocity in the shaft due to the velocity of rotation of the shaft. But it is also whirling like the Earth is going around the Sun. So these two combine to give you the V-rel, which is the V relative velocity of the rotor with respect to the stator. Now, when you put that here, going back to this equation, you will get this V-rel. As you can see here, V-rel is in this term, in this equation. Okay, V-rel is here, and the sign of that will give you the sign of the friction force, which is mu y. Okay, so we have now a set of equation. The problem is that this heaviside function has a issue. This has 0 or 1 as its it's 0 when the rotor is not touching the stator, right? There is no touch, there is no very high stiffness, so that term is 0. But once it touches, it becomes 1 and that term comes. So this 0 or 1 actually causes very strong nonlinearity. It is the on and off nonlinearity, switching on and off the nonlinearity, which is introduced. And this, has no analytical solution, as we know, the nonlinear equations. So is there some way we can make it analytical? Number one. Number two, because of the non-analytic nature, we can do only things like solutions with Ranga-Katta method, which actually introduce inaccuracy, and they are not trustworthy till we verify them experimentally. So this discontinuity which is there leads to very high computation times and leads to inaccuracy. So one of the problems we worked on is to make these functions with some known analytic functions. So one of the known analytic functions, and I'm not saying this is the only function, there are other functions also, is tan hyperbolic function. So if we have this on and off, you can see here on and off, it's a complete discontinuous nonlinearity at its corners, can be modeled with that blue curve which you see, which is tan hyperbolic. But as you can see, this tan hyperbolic curve is not exactly on and off. It is smooth at its corners and it is almost like the shape of S. But what we know from tan hyperbolic is that if we increase this value of k, a constant, and keep on increasing, which is shown in this figure, we will come closer to the on and off. It will never be on and off. As you can see, it is rounded here. So this is an analytic function actually. So one of the things was to study if we can put this smoothing function in our equations there and see if we can have a model where we can do it analytically or which can take less computation time. Okay. Now there is also a 0.5. This is actually because we have offset this whole tan hyperbolic, multiplied it by 0.5 to bring it up such that the top becomes 1. That's the only purpose here. And then we see that very high k at 1000 is when we get. So this is an exercise which was done. We published a paper on actually mechanical systems and signal processing also on this, that if we have very high value of k, then we have a system which is we have a configuration here of this term which is analytic, which takes less time. As you can see, the computation taken time with smoothing function is here. You see that this is about 350 seconds, the red one, and with smoothing function we've gone to about maybe 25 seconds. So this is the order of reduction of computation time if we can use these smoothing functions carefully. So the point is you have to be very careful, because sometimes by using smoothing function you can lose out information on nonlinearity. So the smoothing function has to be, it has to be optimized for this kind of a problem. Okay. So now what is the result of all this? So First thing is, if physically we are looking at rotor stator rub. So if we look at a rotor stator rub, there is first the condition when there is no rub, right? R is less than R0. That means the amplitude of the whirl of the rotor is less than the clearance. So there is no rub. When that happens, we get an orbit of the rotor, which is the motion you see on the X and Y side, is almost a circle. And if you do the fast Fourier transform of the time domain data, you get one frequency, which is actually the unbalanced frequency, ME omega squared cos omega t. This cos omega t, omega is the running speed actually, right? It is not the natural frequency as we would be knowing. So we get that. Now, let us say R increases because of some cases epsilon is increasing, the eccentricity, as I told you, fouling, or it is increasing because the speed is increasing, because it is m mass of the rotor, epsilon eccentricity, which let us say is constant, but omega square. So if you increase the speed of the rotor, then m, it increases by square, right? The unbalanced force, and it starts touching the stator. Now this partial rub, as you can see, will create a condition of this orbit, where you will have actually the the rotor going touching, and the rotor will touch the stator and come back. So there is bouncing taking place, and this creates this kind of orbit, which you can see looks like a annulus, a circle within a circle. It is actually the rotor moving, bouncing off the stator, coming back again, R less than R0. Then again it goes back and hits the stator. So this is partial. And what it shows us is the frequency spectra. But the important thing here, in fact, for this frequency spectra also, all three, is that you can see the frequency which is 0 here, and it is positive till here, and there is a negative side to this frequency. So this is a special thing which is used in rotor dynamics, and it's called a full spectrum. Now, what is a full spectrum? Let us see this. Full spectrum is actually a mathematical decomposition of the whirl of the rotor. Basically, physically saying, and it's given very well here, actually work done by Dr. Muzenska. He was a consultant and the founder of Bentley Nevada. Now, of course, out of it in some other company. But a very good mathematical decomposition of the whirl of the rotor, because any standing wave is composed of traveling waves, one moving forward, the other moving backward. In the case of a rotor, you can have a backward wave which is different in amplitude and phase with the forward. So you will never have a standing wave, as we understand. So in rotors, there can be a case when we have a slow moving traveling wave, not a standing wave. Okay. And if the backward moving wave is stronger than the forward moving wave, you will have a net backward whirl. So breaking down the whirl of a rotor into the forward and backward components mathematically, you get two frequency spectras. One on the negative side, which is the backward moving wave frequency, and one on the forward side, which is the positive side of the full spectrum. Okay. And this is actually a diagram telling how this is done. There are algorithms for this. We developed it. It's a little bit of mathematics, but important for rotor dynamics, because we take two measurements. Okay. And this X and Y, can be put down in complex form as X plus iota Y. Okay. Then the FFT of the complex signal is taken, and then the FFT is performed to shift the zero of frequency component to the center of the axis and the absolute value of FT, and then you get a full spectra. What it tells us physically, the important thing is that if you have components on the negative side, which is the backward whirl. Now, what is the backward whirl here? You see this frequency? This is on the negative side. That means that rotor is vibrating with a negative, it's called a reverse whirl actually, and this is pretty prominent, but it is less than the forward whirl, which is the positive side. Okay, so you will not have a net reverse whirl. You will have a net forward whirl with a stronger, which will not be that strong as is the case here because it is being reduced by backward whirl. Now when you have full rub, which is the third case, that is when the rotor completely touches the stator at very high amplitudes and it doesn't let go, there's no bouncing actually, then you will have a net backward whirl because you can see very strong component of the reverse whirl which is happening, and this is called dry whip. This is a term which is called during rub of the rotor with the stator, it is called dry whip. Okay, now this is analyzed from one of the methods we've used is the adaptive chirp mode decomposition, which actually takes the signal, the time signal, okay, and then uh, what we know of this signal is that there is frequency modulation. Okay, so we are not talking of amplitude modulation. So there is frequency modulation, and we have to find out what frequencies are modulating. So this whole process, this signal processing method, actually finds out the modulation and how the frequency is changing with time. So this is an estimate and this is the real. When this difference goes to zero, this function is minimized. So if we minimize this function for a given frequency, we will know at a given time that is the frequency which is just for a little understanding, what is frequency modulation? If this is time and this is amplitude. So frequency modulation would be if the time domain result would be, plot would be like this. Okay, then it would become closer, then again further. This is frequency modulation because at some time you have one frequency, at the other time you have a larger frequency. Okay, so this is a frequency modulation which is different from amplitude modulation, which would be like this. Same frequency, but the amplitude is modulating. Okay, you can see amplitude modulating same frequency. But in this case, you can see closer, higher frequency, and then lower frequency. This is frequency modulation. So this is what is happening in our rub, and we need to find out the frequencies which are modulating this. Okay, so this frequency modulation frequencies are determined by this method of adaptive chirp mode. This is taken, of course, from one of good work being done by published in Journal of Sound and Vibration here. Okay, this is not our work. We've taken this for using it in our rub model. Now, what is the results of this? So let us say periodic case when there is no rub, right? The first case which we just saw. Then we will see this is the waveform. There is no frequency modulation here. You can see there is no frequency modulation in this case, and the orbit is a circle. So you have a single frequency as we know in this case. And when we do adaptive chirp mode decomposition, we will find a single set C1, and the other which modulates is very small, almost zero. You can see 10 to the power minus 13. So there is no frequency modulation. Okay. So this, when you plot on a spectrogram, which is a plot of frequency versus time, you will see a constant line because there's just one single frequency which is not modulating. Okay, it's a straight line we get. Now when we get onset of rub, which is the case, second case which we just saw previously, when the rotor was bouncing off the stator. Now in this case you will see not only amplitude modulation here of the time domain, and of course this band which was the rotor vibrating bouncing of the stator, but now you will get the main frequency and also a nonlinear frequency, two frequencies coming. As a result, when you do adaptive chirp mode decomposition, you get, this is the main frequency which we were getting in the no rub case also, but now there's a component which modulates it, the frequency, and it is not small now. You see, it was 10 to the power minus 13 here. It has increased significantly by the order of 10 to the power 10 to the power 7 actually. Okay, I'm sorry, 10 to the power 8, 10 to the power 9. Okay, it has increased by so much. And so it is prominent. As a result, this frequency spectrogram which we see is not a line here, as we saw here. It is the line itself is so that the frequency is changing with time. It is modulating. This is the frequency modulation which we start seeing on this partial rub case. Okay. So now what these things are telling us is that, when the rotor rub happens, you will go into cases of instability, stability. Instability is not good for a rotor system. It will lead to that photograph we saw where the system has broken off and the engine is on fire. So what is, in terms of a theory, how do you find out a system has become unstable, especially a nonlinear system? Well, a nonlinear system, one way is by flow quit, which you would have done, many of you. If you have the time domain response, you perturb it by yt. Okay, and now this perturbation itself gives us a new equation in state space form, and you create you run a Rangakatta on this with the initial condition as the unit matrix of size of the this state space, and then get this, which is called the monodromy matrix. The eigenvalues of this matrix, you can see the initial condition is the the identity matrix of the order of the state space system we have here, and we get phi. The eigenvalues of this phi now gives us the idea of stability. This is, in a nutshell, the algorithm for stability analysis of nonlinear systems. And the eigenvalues of this monodromy matrix are called flow-quit multipliers. Okay, they are like telling you whether your system, as you can see that your system is actually X here and Y vertical, but your system is running in time, right? We have this dimension of time is very important for us in dynamics. So any orbit, if I can just draw another picture of this, the orbit of a rotor would be given like like this. It won't be a closed circle, but it will be a spiral like this. And when you see it from this side, you will see a circle or two circles. You can see one circle like this, or you will be able to see another circle like this, which tells you there's another frequency. So now this flow-quit multiplier is telling you that at any instant of time, if this starts increasing, it starts becoming unstable. So this gradient of this change here is, the orbital convergence or divergence, which is coming out from the flow-quit multipliers. And what this tells us is, after we find out the eigenvalues of the monodromy matrix, that if these lie within a unit circle, then the system is not diverging, it is not unstable. If it lies outside the unit circle, that means it is diverging and it becomes unstable. So then we introduce the Poincare map, which again is something you must have heard about and also used it. This Poincare map, when we study, gives us a feeling whether the system is periodic. It is periodic with other time periods, 2t, 3t, or is it quasi-periodic, where there are frequencies which are incommensurate. That is, if you divide them, you will not get an exact integer. Or it is chaotic, when you will not get any form, you will get a certain fractal nature of the response. So, the conditions in the algorithm are, if flow-quit multiplier leaves the unit circle through plus one side, it's a saddle node bifurcation. If it leaves the unit circle through minus one, it's period doubling. And two complex conjugates leaving from the imaginary axis, it's a Hopf bifurcation, actually, here, which is the case for us in the rotor stator rub. Okay, so this is just explaining the eigenvalues of the monodromy matrix, and if they go out of this through the negative side, you can see the complex conjugates there. The imaginary axis is there on the y and the real axis on the x. You will see a case of Hopf bifurcation, which will, on changing the speed or some parameters, it will finally lead to a chaotic response. Okay, and these plots are actually from the results we've run or for our case. So the whole point is that from this study is it's very important to avoid this kind of unpredictable. Actually, chaos is in a way predictable, in a way unpredictable. But it's not a random thing, right? It's not noise. So we should not say chaos is noise. And that is the problem with application of nonlinear dynamics in diagnostics. If you go in an industry and start talking about chaos, people will get very, very alarmed because it is very difficult to detect chaos in general. And the second is most of the problems are noise. So they will say, no, you just reduce the noise, which is the amplitude, forget about chaos. But there are industries like aircraft engine, the aerospace industry, where after you have reduced the noise, removing it, then you have to study whether it is chaotic or quasi-periodic or periodic, and then go and modify the design. So the whole purpose here is to study, the chaos with the noise, and then increase the distance between the main frequency and the nonlinear frequency, which I showed, which is called the dry whip onset frequency, the gap between that, which is causing frequency modulation. So if we increase this on the yellow side, all the points on the yellow are going to give you more stable response. If you go to the blue points, which is these blue points, this combination of damping ratio, stiffness ratio, and friction coefficient is going to give you more unstable response. Okay, and it can lead to chaos also. So this is a very good 3D parameter which has been made by my student actually, who's published this paper, and a very good design for hand out for an industry where they need to have damping, stiffness, and friction coefficient for a rotor which can touch a stator. Okay, so that we can avoid unpredictable responses. So, talking about chaos in nonlinear dynamics, we need to understand what is the effect of noise, right? And also, how can you separate it? Separating noise from nonlinear response is very, very difficult because the usual methods of filtering actually will take the data, you acquire the data, you apply filters. As a result, the nonlinear dynamics will also be destroyed. You will never come to know whether your system is quasi-periodic or chaotic because you applied a filter. You might have reduced the amplitude and said that everything is a noise, but that is not true. So this is another exercise which we are undertaking in finding out what are the methods such as 0-1 test for chaos, looking at the fractal dimensions, and then using some visual representation to see what kind of nonlinear response we are having. So Lyapunov exponent, as I told you, tells you the convergence or divergence of the trajectory of the system in 3D in the real world. Okay, it is given by this exponent lambda. If this is positive, then lambda I, the Lyapunov exponent, will diverge. If this is negative, it will converge. So you can understand from the basic definition of stability, positive Lyapunov exponent is indicating instability, and the larger the order of uh, this Lyapunov exponent, the stronger is the nonlinearity. So if your Lyapunov exponent is something like 100,000, you have a highly chaotic system. If it is 1, 2, it is chaotic, but it is not that strong. Okay. So we took some, parameters of mass, K, mu, clearance, the eccentricity of the unbalanced eccentricity. Then we took the stiffness of the stator and different values of damping and different rotational frequencies from these two equations of a rotor and ran all these methods to find out what is the different kind of responses we get. So if you see the displacement and the orbits for a case where there is partial rub, you can see the rotor going and touching the red circle, which is the stator, bouncing off then coming back again, then bouncing off, coming back, and this is the orbit you get. Okay, this actually gives you partial realm chaotic motion where you have these prominent frequencies, but in between here you will see band of frequencies. So many times, when you do this simulation, you will confuse this to be numerical noise. But actually, if you plot the Poincare map, you get the very characteristic fractal or the layered structure of the chaotic. So this is a visual representation which for the cases we ran for chaotic system. Okay, and this is of course a simulation. Now, as I said, that when you do diagnostic of rotors and talk about chaos, people won't take that so easily. So, uh, the given is the reality is that there will be noise in the system. So, if there is noise with chaos, what are the systems to detect it, especially in algorithms? So, there's called a 0-1 test, which is used in physics. Actually, a huge, physics deals with a lot of applications where there is huge amount of nonlinear dynamics, as we know, right from some very huge scales in astronomy to small scales in atoms and subatomic particles. So this 0-1 test was actually formulated by in this paper from the CIM Journal on Applied Dynamical Systems. It assumed that noise and chaos are the same, which is not a good assumption, of course, because that is what we are trying to. But what it does is that if you have a given set of data, without going for very expensive Poincare maps, by the way, Poincare maps are very expensive because 1 million set of data will produce one Poincare map, and huge amount of computer resources are taken. So can we just have a time domain data, do some test and find out whether it is periodic or it is noisy or chaotic? So that differentiation, this 0-1 test for chaos does. If it is 1, that means it is either noise or chaotic. If it is 0, it is periodic. Okay, so when we do this test, the limitation is that we found a set where the 1 means it is either chaotic or random, which has noise. So as you can see, in the problem with this method is that if we have a periodic motion with noise, as you can see, when we do this method, we will see something like chaos, but that is not true. Okay, so now we need, this is a quick method of understanding whether there is chaos or quasi-periodic or no, or noise, but it is obviously absolutely not sufficient for us because we can't equate noise with chaos, because if we are trying to reduce chaos or quasi-periodic motion, we have to work on some design features which are not the same as those for noise. So now we will try to do work through the challenges. So if you see the challenges of noise and chaos, they have similar statistical properties, and most of the methods we discussed, Lyapunov, exponent, 0-1 test, fail to differentiate. So the problem is that the standard noise filters, as I told you, will completely destroy the chaotic data, and you will never be able to know whether it is chaotic or quasi-periodic. Also, they look the same, noise and chaos. They have broadband frequency spectra. Okay. So below a certain signal to noise ratio, the signal loses its properties and cannot be recovered with filters. This is the important thing. So what do you do now? So we do something which is called a composite test for chaos. This is another paper which has now been published in nonlinear dynamics from our side. So we get the Poincare map, perform 0-1 test. If it is 1, that means there is either noise or there is the chaos or quasi-periodic motion. So we find that out in this box, whether it is chaos through this method, which we will see in the next slide. And do this, Euclidean distance, ED is calculated. And there is a certain box we generate, which we'll see in the next slide. And that, if it is outside, it is non-linear. And then we do nonlinear denoising. This is a method, again, taken from physics, from Schreiber's. It is called the Schreiber's filtering for nonlinear systems. And then redo the 0-1 test. Now this method is devoid. Here we have made the system data uh, devoid of noise. Either it is chaotic or periodic. And once we do 0, 1 test now, if it is 1 means it is chaotic. And if it is 0, that means it is periodic motion. So this is a method which we've applied in algorithm, and that BLCT test is called the Benford's law. Now this is an interesting method because Benford's law, you would have heard of it in the news for things like the American election last year where there was so much of controversy. So they were taking the data to find out whether that data is actually noise or somebody's tampering, right? This is what the problem in America was, that one party was claiming they are, the whole votes have been uh, tampered with, something which we used to hear in India some years ago. So then the Benford's law, and this we found in the news report actually, that they were applying the Benford's law, finding out whether it is noise. So we applied this Benford's law on our noisy data. And this, what this method tells you, and you can very easily go back today and check on this, it's a very simple law which is being used. That Benford's law, actually, if it is being applied, on noise, is uh, scale invariant. So if this scaling is done S of different levels, you will get the same shape of the Benford's distribution, which is, as we saw in the previous curve, the amplitude falls down like this, okay? And the Euclidean distance for noise is almost scale invariant, while for chaotic data sets, the deviation is very significant and increases with scale. So this Benford's law is another method for checking out if your data, time domain data from the rotor, is noisy or it has a chaotic set. So you will see in the next plot now. You can see this. The blue is showing you the data for a noisy data with noise only. You can see it going like this, down, the blue, and the red is not going, it is going up, down, and then up again. So this red is the same case which we've done in the previous, which has chaotic data. So let's say we never knew what that data is chaotic or noisy. If we apply the Benford's law for a chaotic data, it would not have this exponential drop like the blue bars. Also, what we do is we find out the Euclidean distance of these curves, and if this Euclidean distance remains the same, scale invariant, within a box, this is called the box technique, then we say it is noisy data. But if this Euclidean distance changes with the scaling factor, scale variant, then it is indicating a chaotic data in your system, okay? And so, this is another method, BLCT method, which we've applied. And then this, I explained to you about Schreiber's nonlinear noise reduction, where we have applied it to a Poincare map. As you can see, this is a seemingly, a chaotic data. It is true that it is chaotic, but with this kind of a plot would be difficult to, it might look like some continuous curve also like this, but it is not. Once you do nonlinear Schreiber's method for denoising, you will get this fractal, this layered structure of a chaotic response. Okay, so this tells you that we need to do nonlinear noise reduction not in the original data but in the Poincare. If you do any kind of filtering in the original data of the rotor, you will end up with completely distorted data from which you can extract nothing. So you have to be careful. Again, a method which is used extensively in physics. It's in the Physical Review journal. Okay. So here's an example. There's a Poincare map we got with noise. Okay. It doesn't give any indication whether it's quasi-periodic or chaotic. We applied the denoising and we saw this. This is a quasi-periodic, indication. It's a closed loop like this. We applied to this another set of data and see what we got, a single point, which means that it is actually a completely periodic system which looked like some noisy or chaotic or quasi-periodic, but by applying this technique, this is, uh, periodic. So this method also has to be used in condition monitoring of rotors for critical systems where, we need to understand whether the system is quasi-periodic or chaotic. So if we sum up the composite test, Then we have the Benford's compliance law test, the boxing, which I told you. The boxing means the bounding box, and then the 0-1 test, and then the signal mixed with noise. We need to do some non-linear filtering of this. Okay. So now there's a huge lot of things where it is applied, not just for rotors, but components of rotors such as gears. Now, gears are systems which have time varying stiffness, and this is a work which I have taken, a slightly old work, but excellent work on gear dynamics, both theoretical and experimental, from Professor Kaharman of Ohio State University, where they have modeled this as a time varying stiffness, and this will lead to huge issues in terms of the prediction of the response using Rangakatta method, which, as I told you, not will not give by itself. It doesn't stand verification. It needs verification with an experiment or some other method. But this time varying leads to, in fact, they've done some very good experiments also with this rig. It leads to, the very interesting jump phenomena in nonlinear dynamics. They have shown this at different superharmonic levels. It is jumping, and you can see with great details they have got the main frequency, the nonlinear frequency, similar to what we were getting in rub. Although rub is also a case of partial rub when the stiffness is changing with time. Okay, but this is a parametric system which we are dealing with, similar to a ball bearing system, which we'll just see. So this leads to a chaotic response. And in 1997, no Benford's, no 0-1 test, no nonlinear. So this has not been done, what we are doing now, in finding out whether this is really chaotic or whether this is quasi-periodic or periodic, maybe. It looks like chaotic. Of course, you can see this frequency spectra, broadband. Okay, so this leads to a very interesting thing in nonlinear dynamics of mechanical system called intermittent chaos, which is very common for fluid dynamics. Okay, you open your tap slowly, water tap, and you will see very smooth flow, and then you keep on opening the fluid flow, it breaks, and then it again becomes smooth, breaks, again becomes smooth, right? This is probably an experiment you've done probably in your taps, or you would have thought about it. This is called intermittency. So forget about fluid dynamics. Even in systems like gears and bearing, it exists. Okay, and you have a response where you have a chaotic response. Then there's a steady state response broken by chaotic, again becomes chaotic. So in time, and there are different kinds of intermittencies which are defined from the Hopf bifurcation, which we were dealing with. So this is, detected by Professor Karman in gears, and I saw it on bearings from my work some years ago, in ball bearings also, mostly from simulation. Okay, so you can understand from the, when you see this kind of signal, how much noise and vibration and a problem in terms of fatigue life this will create. So we have to avoid this. We have to avoid the set of parameters which results in this kind of motion. And this is true for ball bearings. This is my work actually some years ago, actually my PhD work. So you have these balls going around. You get this stiffness, which is a function of time, similar to the gear system, where it is a parametric system. And you will get this, we tested it out, the Rangakatta, with this harmonic balance method. As I told you, Rangakatta by itself, people don't trust. So this is another method, analytical method we tried out to compare it. And then we got this chaotic response here. You can see this layered structure and the intermittent response, which you see here. Okay, so we saw intermittency theoretically in ball bearings. Now, going to some more application, sources of nonlinearity. This is another work we've done actually for the Aeronautical Research Development Board, where we had this squeeze film damper, where this is the gap in which oil is filled, and as the rotor runs, this gap pushes out oil. It works like a damper. Okay, this whole thing is made with a EDM machine, and these are called actually integrated squeeze film dampers, and they have been studied in great detail. You will find some very good publications in ASME, But this, what we have done is slightly different from that. And we found that if you don't have the optimal clearance and thickness, this is the thickness of this, see the next slide, this is the thickness, and the clearance is of course this small clearance here. If you don't have the optimum this thing, you will get a nonlinear response. We tested it out on the rig here with proximity probes, a small rig which we could work on. This is the squeeze and damper support, bearing support here. And we got these kind of orbits and high nonlinearity for certain combinations of clearance and length, where we have these 1x, 2x, 3x, 7x, okay, leading to orbits which are not circles actually. We get these very non-circular orbits, almost rectangles, okay, look very strange, but this is what is happening. And then if we change, make the combination of clearance and length more, you will get a very high level of nonlinearity, okay, where the orbit is almost like a rectangle with smooth edges actually. So this is the point in terms of various sources, and there are many other sources, but this is some example of nonlinear sources which we worked on. And if I can just conclusion has just 4 points, but it gives you that there is a huge lot of work which is required, because rotors are very important for technology at this point of time. There can be a lot of sources of nonlinearity in rotor systems, and study of vibration and its dependence on parameters from these critical system is required for avoiding dry whip chaos. And then removing noise from chaos is a difficult process, but it is important. Otherwise, we'll miss out the important things in the data, and we'll be either overestimating, making high safety factors, or making our life also very boring, because we won't be dealing with some interesting things like will be a usual rote of the work and not having innovation. Because when we can go into details of this kind of analysis is when you will be able to innovate and think of new things. Okay, so I'm just about taking more than an hour, I'm sorry, but that's all I have. Thank you very much. If there are questions,
Yes, any questions from the participants? Well, sir, actually, whenever we talk about the linearity in non-linearity in this particular case, I think is it really a geometric non-linearity, or to some extent material non-linearity will also come into picture here, sir?
what we are talking of is geometric nonlinearity.
Okay.
But what I have not talked about is some other work we are doing where actually springs which are used for supporting rotors, because of the material changing its properties due to very high strain rate, you can have material nonlinearity, which is a function of time. So both are there. But in this case, whatever I have described to you, it is mostly geometric nonlinearity.
Okay, sir. Sir, and in a very simple sentence, how to differentiate between chaos and noise?
Yeah. So, you know, as I've said in this presentation, it looks like noise, the chaos, right?
Yes, sir.
But it has a certain feature which is predictable, which is that layered structure. Okay, you can see this layered structure here. It is not going all over the place, that is noise, but it is falling along some lamina. Now, whether at time t it is here, at time t1 it is here, but it is close to this line. You see that?
Yes,
So
sir.
there is some predictability we have.
Hmm.
And the second thing is that uh, noise is generally coming because of extraneous sources, right? It may be the noise coming through the ground, it may be aerodynamic noise, but the chaotic response is mostly coming because of the inbuilt parameters.
Okay.
So you can reduce chaotic response only by design changes.
Okay.
right? Changing the stiffness, changing the damping.
Right.
But noise in general can be changed by changing damping or isolating the structure, or maybe the extraneous, removing the extraneous sources. So
Okay.
let us say it is chaotic plus noisy both, and you have the system where you run it. So you think it is noise because of the surroundings. So you isolate it, maybe you put it in vacuum, okay? Then you isolate with dampers, but still you get something. That
Yes.
means it is going into some nonlinear response
Okay.
where the internal dynamics of the system is creating this kind of response. So, the two are different. There is no doubt about it, but they look the same. And when we go into details of the modeling, the mathematics, and the way we do the signal processing, as we've tried to do in this case,
Yeah.
we will have different results. So
Okay.
that's my answer. I hope that's a little bit clear.
Okay. So can we say that the chaos is related to the design of the equipment?
You're right, absolutely.
Okay.
So, but then you can also say that the noise is coming because of the clearance, and clearance is a design parameter,
Yeah. Yeah.
right?
Yes. 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 Yes.
Yeah. So, see, the point is these kind of things, there is no clear answer,
Yeah.
but the clearance is going to give you chaos also. For example,
Okay.
the stator and rotor rub is happening because of clearance R0.
Right.
So now when it there is nothing there, let's say there is no fluid, and it starts rubbing, okay, in an aircraft engine, when the blade is rubbing against the stator, there is wind also blowing, right, air at very high velocity, that is
Okay.
creating noise. But let us say there is some rotor where it touches the
Yeah.
stator, then the response you will get will be mostly from will be chaotic and the internal nonlinear dynamics of the system, and you will have to change the design for that.
Right. Right. Okay. Any other participants? Any queries from the
Hello,
participants?
sir. Hello,
Yes.
sir. Thanks for the nice presentation. Sir, this applications that you have mentioned is in aircraft scenario. Can this be extended to other applications which are not so trivial?
Which are not so trivial or which are trivial?
Like in the sense, yeah, because aircraft it is very critical, but can it be extended to other works, other applications?
Absolutely. I mean, see, the fundamental thing which we can, which I have tried to, explain is that we are talking of rotors. Okay. I can talk of non-rotor systems also, but I'm not doing that. So in rotors, you can have it in a turbo pump like the GSLV cryogenic pump, right? So that's not a gas turbine. You can have it on a turbocharger, which is on a maybe a IC engine. Okay, I gave you the very interesting example of very few people know X-ray tube rotors also, where there can be strong nonlinearity because X-ray tube rotors have high temperature, 300 to 400 degrees. Actually, the electron beam produces huge amount of heat, and vacuum means there is no lubricant, so everything is dry. Very strong nonlinearity. So the same thing can be applied there also. So yes, you are right. It can be applied.
Okay, thank you, sir.
Sir,
Yes, yes.
I think one last question, if you can take up.
Yeah, yeah. Please.
Sir, actually, what this negative frequency does mean, because this is a typical word we come across in this nonlinear phenomena. Actually,
Yeah. So I will try to draw. Hopefully it comes out well. Just a minute. Very short drawing. Okay. Uh, okay. So, any vibration we talk about is actually, just a minute, please. Any vibration we talk about is, let's say there is a string and there is another wall, and we give energy to the string, so it will vibrate like this. It will move up and down, right? And this is a traveling wave. right? So this point will go down, this point will go up. So each point has a motion which is from amplitude, mean, and the opposite amplitude. Is that clear? Is my till now clear what I'm saying? This is a traveling wave which is traveling with a certain
Yes,
speed,
sir. Yes,
right?
yes, yes.
Now it hits a boundary and reflects back.
Ah,
So you have a reverse wave now.
okay.
Okay, this reverse wave will in general be will go back like this. Now if it is in the same phase as this, so the two will actually magnify. If it is in opposite phase, it will actually lead to a standing wave, right? So you will have points like this where these points will become nodes,
Yeah,
and
stationary
this will
cells.
become antinodes.
Right, sir.
Now these are standing waves, which are the
Yes, sir.
general vibration system. We take this, but for some very specific vibratory system like rotors, the two are not in the same phase and of the same magnitude, so the wave is always traveling back and forth.
Okay.
There is always a traveling wave,
Okay.
okay, which means that the rotor, if we see, has a whirl. So this is your rotor, it is whirling. It is also rotating like this. As I told, the earth is rotating on its
Yes,
axis,
yes,
it is moving.
yes,
This
yes.
is a combination of green, let us say this is forward wave vibration, and also there is another vibration with that, which is the backward,
Ah,
like this,
yes.
backward traveling wave.
Mm.
Now, in case of rotors, it can happen because of asymmetry, because of stiffness changes, that the red is wave is not of the same phase and magnitude, amplitude as the green. So you can have a net green wave because it will red will reduce the green, or if red is very strong, it will reduce the green wave, and then you will have. So it is very interesting that the earth rotates in a clockwise direction, anti-clockwise, as we are seeing, and it also rotates around the sun in the same direction. That is called synchronous whirl, right? That is called forward travel. But there are applications, especially unstable applications, where the rotor rotates like this but whirls in the opposite direction. This is called backward whirl, and this is the negative frequency backward whirl, and it is a unstable state.
Right.
If you perturb this state by a little amount, the whole rotor system will break.
Ah.
So you have to avoid this. So do you understand what I'm saying,
Yeah, yeah,
Dr.?
yes, sir. Yes, sir. Yes, sir. Yes, sir.
Yeah, it's not easy. I've just tried to explain actually.
Yeah, yes. Okay. So, thank you, sir. You have uh, discussed a very complex research in your talk, and it's very we are honored to have your lecture. You discussed the comprehensive introduction to the development of turbines, rotor dynamics, machines, importance of non-rotor dynamics in rotor design, and the concept of whirling, and the contact forces, and most importantly, the Floquet theory and the stability criteria, and last that very interesting Benford's law, and you have enlightened the audience with this wonderful talk that you have been on this nonlinear dynamics in rotors. And so thank you very much, sir. Thank you very much for your time and effort. And from my side, along with my friend and uh, coordinator, Dr. J. Anjaneyulu.
Sir, thank you very much, sir. We are honored with you for lecture. Actually, you are enlightened so many things in this. I think if you are given some more time, you should have just wait still further. Anyway, we are happy to have like a tremendous great lecture, sir. Thank you, sir.
Yeah, thank you both of you and everyone for listening patiently to me. It's been a long talk, so thanks everyone for listening to me,
Yeah, yeah.
and
Yes.
and for the very nice questions.
Yeah. Thank you, sir. This is Bhanu Prasad, and I will contact you later, sir. Thank you.
Okay, thank you very much, Dr.
Thank you,
Bhanu.
sir.
Thank
Thank
you,
you. Thank you.
everyone. Bye.
Thank you,
I say
sir.
thank you. And all the audience, please stay back. We will join the other session. The link is shared already, and Dr. B. Venkatesham is already there waiting. So please uh, join with the new link that is provided to you.
Thank you.
Okay, thank you.